Welcome to Maths with EJD. We continue with Laplace transform, and still in the spirit of stability, we're talking about Laplace transform, the Routh-Hurwitz criterion, and stability. So in the previous video, we had talked about stability in the general sense of getting the poles of a transfer function for a Laplace transformed system. Okay, so here, let's look at how this connect together. Of course, the first part is the Laplace transform, which we've been talking about a whole lot, but it doesn't harm to, always refresh our minds about what that stands for. So the Laplace transform is an integral transform. So another example of an integral transform is the Fourier transform. Interestingly, the last video on this playlist is going to be comparing Laplace and Fourier transforms. So the Laplace transform is an integral transform used in differential equations, control systems, and signal processing. It converts functions of time into functions of a complex variable S, simplifying analysis. Okay, now let's look at the definition and some key properties. So definition, of course, this is well known already. I've said this a lot of times. The Laplace of a function f of t is always given by is f of s, which is now integral from 0 to infinity of e raised power minus st f of t dt. So we've done this a lot. So I'm talking about some key properties. Um, key properties. So one of the properties is linearity. So linearity simply implies that if you have the Laplace of if you have the Laplace of a f of t plus b g of t, it's exactly the same thing as a fs, af of s plus b g of s. That means um, the Laplace of a sum is the sum of the Laplaces, so to speak. Okay. Then we have the idea of differentiation. Differentiation. So for differentiation, right, if you have the Laplace of f prime of t, it is simply the same thing as s, f of s minus f of 0, the initial condition. Okay. Then we have integration. Integration. So if you take the Laplace of an integral, so the Laplace of integral from 0 to t, integral from 0 to t of f of tau d tau, that is simply f of s. That's the integral of the function, f of s, and that now divided by s, basically. And we also have time shifting. Time shifting, that's another property. I mean, I did a comprehensive thing on these properties in the second video in this playlist. So this is just more like a refresher. So the Laplace of t minus big T multiplied by u into t minus t. So if there's a shift in time by t, then we just have e raised power minus s big T, then the Laplace of the original function. So that goes. All right. So would you well, if I'm going to talk about examples here, right? So I'll just say um example, okay, example, find the Laplace transform and the Laplace transform of f of t equals t squared e raised to power minus 3t. T squared e raised to power minus 3t. So here we just answer using the formula. So if we use the formula that the Laplace of t raised to power n e raised to power minus at is simply the same as n factorial all over s plus a raised to power n plus 1. Okay, we have, so if we use that formula, we'll simply have that f of s, I mean, all of these have been done in depth previously, so no worries. So our n in this case, so for f of t, we have for f of t equals t squared e raised to minus 3t. So what we simply have here is, so here, our n is 2. So 2 is n now. Then a is 3. 2 is n. A is 3, basically. So we just have fs is now n factorial. That's 2 factorial all over s plus 3. So 3 here is minus. So we have s plus minus 3 raised to power n plus 1. So that's 2 plus 1. And that's equal to 2 factorial all over s minus 3 raised to power 3. So, and that's what you get for that. I mean, we've done this a lot, so there's no point stressing too much about it. So I come here and then I go here. Okay. So let's go for the Routh-Hurwitz criterion, which is more like the focus here in this, talking about stability. Roth, Routh-Hurwitz, Routh-Hurwitz criterion. Okay, so the Routh-Hurwitz criterion determines system stability by analyzing the sign changes in the what is called a Routh array, in the Routh array derived from the characteristic equation. So normally what we would do is we equate the characteristic equation to 0 and find the poles. But when you have complicated systems where it's difficult to do that, then the Routh-Hurwitz criterion becomes really useful. So what's the procedure for this? For the Routh-Hurwitz criterion, the first thing we want to do is to write the characteristic equation. You know, you get the characteristic equation after you take the Laplace of any system you're given, and then you end up getting, when you solve for y of s, so the denominator becomes the characteristic equation of the system. So p of s is now an s raised to power n plus an minus 1 s raised to power n minus 1 plus all the way down to a1s plus a naught, a constant, plus a naught. So so here it's important to note that so write the characteristic equation, right? So let me say number 2 now. Number 2, the first two rows contain coefficients from p of s, that p of s up there. And then number 3, subsequent rows contain coefficients from, oh, subsequent rows, right? Subsequent rows are computed using determinants. using determinants. And we came across the idea of determinants starting from matrices. That was the very first playlist on this channel. So we have B of I equals the determinant of an minus 1. No, you take note that an minus 1 is the second coefficient, right? So an minus 1, an minus 3, that's the next one after that. And then an down here is the very first one. And then an minus 2. Okay, no. You have an minus 1, then you skip 1, you go to an minus 3, then you come down, you have the very first one, and then the next one after an minus 1. So all of this now divided by an minus 1. So that's the second determinant is really important in this situation. Okay, so once that is done, you should also pay attention to the fact that um, number 4. So we talk about number 4, talking about the procedures, right? So let's say number 4, we have the conditions. Let's talk about the conditions for stability, since that's what our concern is. So no sign change. If there's no sign change means we have a stable system. No sign change means we have a stable system. That's no sign change in the first row. That is. Then number 2, K sign changes. So if you have K sign changes, it means there are K unstable poles. K unstable poles. I mean, this you should have got easily. I mean, this you should have got if you equated the characteristic equation to 0 and solve for S. But when it becomes complicated, that's something difficult to do. So let's go for worked examples. Let's take example 1. Example 1. So um determine 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 the stability of a system whose characteristic equation whose characteristic equation is that is after you've taken the Laplace and you've got the characteristic equation, and it's now S3 plus 5S squared plus 8S plus 6. So from what we got up there, right? When we talk about the solution, just make a table, okay? So make a table. You have the highest power S3, then you have S2. I guess we need some space actually. S3, S2, S1, and S0. That's talking about the constant, as you can see. S3, S2. Now, carefully you need to put those values here. So here we have the coefficient of this and this. Those are the two we have. Anything. So you jump over them like that. So the first one here, the coefficient of S3 is 1. Then that's for the first column. For the second column, you have the coefficient of that is 8. You also have that. So next, you have the coefficient of S2. So that will be about 5S squared and the next one. So you see, this is more like you have a, what did we call that the other time? This is more like, how did you say it? So this is like A naught, if you like. And this is, not really A naught. This is AN, sure. And this is AN minus 2. While now, this will be A, that's AN minus 2, right? And this now will be AN minus 1, okay? AN minus 1 now. That's the second one for sure. That's the second one, yes. So that's 5 and 6. So you have 5 here, and then the 6. That is AN minus 3. You have this is the coefficient is AN minus 1, AN minus 2, and AN minus 3. So we have AN minus 1, AN minus 3, and this is 6 right here. So that way, now that's all we have from the table. So what we now need to do next is to compute the other things. So we can have this and then this. So we need to find this. Okay. So, and the way to do that, we already have the formula, right? So the formula tells us, so let me use green for the things we have to compute. So the formula tells us that we have an minus 1 times an minus 2 minus an, we are taking the determinant, an minus 1 times an minus 2 multiplied by an times an minus 3, like that. So that means we are going to have an minus 1 times an minus 2. So that means we have this, that will be 5 times 8, 5 times 8 minus 6 times 1. That's an, or let's say 1 times 6, just to follow that faithfully. That's 1 times 6. So this now, divided by an minus 1, which is 5. So if you do all that, right, you get 40 minus 6, that's 34. So this is simply 34 over 5. Okay, so this is, so, okay, I guess I want to do it outside. So, okay, since we are not using this place, I'll just say, um, that's an. So we have an minus 1 multiplied by an minus 2 minus an into an minus 3 all over an minus 1. Okay, so that means we have 5 times 8 minus 1 times 6 all over an minus 1, which is 5. So that is 40 minus 6 all over 5. That is 34 over 5. Okay, so this is just 34 over 5, like this. So that is settled. Now, we need this one also, but the thing is, we don't have anything here. So normally, if we are going to get this, we need to be shifting to this place and this place. But since there's nothing there, that would just be 5 times 0 minus 1 times 0 divided by whatever. So this will just be 0, like that. Okay. Now, when we come down, we can get, we want to get this one now. Okay. We want to get this one. And how do we do that? Again, we do just the pattern we have followed now. So I guess I want to switch over to this. So we now need to do 34 over 5 times 6 minus 5 times 0 divided by 34 over 5. So we have 34 over 5 times 6 minus 5 times 0 all over 34 over 5. That is simply 6 times 34 over 5 divided by 34 over 5. So this cancels this, and we just have 6. So this place will be 6. And of course, since there's nothing there, 34 over 5 times 0 is 0, minus 5 times 0, that's also 0. So that goes, okay? So these are the two things we have found now. So we have found this and this based on the original stuff. So with that in place, we have our table complete. Now, the next thing we want to check is in the first column, this is first column, and this is second column. Okay, first column, second column. So from the so you are going to focus on the first column now. So in the first column, in the first column, we have the numbers we have there. That's 1, 5. What's the next thing? 34 over 5 and 6. 34 over 5 and 6. So you can see everything is positive. This one is positive. This is positive. This is positive. This is also positive. So since that is the case, so you can say since there are no sign changes, okay, the system is stable. Okay. Since there are no sign changes, the system is stable. Okay. Like I want to do another example to really drive the point home. I need you to get it very clearly. So let me switch over to this now, while this can go to this. Okay. So let's take example 2. We want to take a fourth degree characteristic equation. Example 2, talking about a fourth degree characteristic equation. Okay. Um, so in this case, Using this. Okay, see what are we using now? I want a fourth order thing. So investigate the stability of a system whose whose characteristic equation is P of S equals S raised to power 4 plus 3 S cubed plus 3S plus 3S cubed plus 3S squared plus S plus 2. Okay, so that's what we need there, what we have there. Now the question is, so here now we have, as usual, we can see that an is equal to 1. That's the coefficient of S4. Then an minus 1 is equal to 3, as you can see. And we have an minus 2 is also equal to 3. Okay? An minus 2 is also equal to 3. Then an minus 3 is equal to 1. You know, that's the coefficient of S. And an minus 4, an minus 4 is equal to 2. So with this now, we can make our columns, right? So we start from S4. So we have S4, S3, S2, all right, S1 and S naught, like that. So we have first column, first column, okay. Then we have second column. Then we also have third column, third column. So we can keep going with the columns, but let's see what we have. So of course, here we are going to have an minus an here. So we have 1, then we skip. So we have this, this, and this. So that's 1, 3, 2 for the first row. Okay, 1, 3, 2 for the first row. So this is an minus 2, and an minus 4. Then for the next one, we have, so we now have an minus 1 and an minus 3, only those two. So that this will be 3, all right? This will be 3, 1, 0 now, because there's no an minus 5. So this is an minus 1, an minus 3, and this is an minus 5, because there's really nothing like an minus 5. So that will be 0, okay? So with this in place now, then we do what we did the other time. Now we have it's clearly understood now. Okay, I guess I want to make these lines just okay. Yeah, I want those lines to just be exactly what we need. This, 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 and this. Okay, exactly this. All right, so I can do my calculations by the side. So first of all, we need this value and this value. So for this first one, right, we know it has to be an minus 1 times an minus 2 minus an times an minus 3. So that would be 3 times 3, okay, minus 1 times 1 all over 3, all over that an minus 1. So that's 9 minus 1 all over 3. That is simply 8 over 3. So the result here is 8 over 3. So this is 8. This is 8 over 3, like that. And then next, we want to get this. So how do we get this? I think this should be easy, actually. So this is 3 times 2. All right. This is 3. So this should be 3. I mean, this one now. It's 3 times 2. This 3 times 2 minus 1 times 0. So that's 1 times 0 all over that 3 we started with. So that's 6 minus 0 over 3. That is simply 2. So it means this place is 2. Okay, that's 2. Of course, if we go further, because there's nothing here, so this automatically this will be 0. Now we go down. So the next thing we want to get now will be we want to get this and this and this. Okay, so how do we get that? Again, we go 8 over 3 times, so that will be 8 over 3 times 1 minus 3 times 2 divided by 8 over 3 again. Okay, so let's do that. So that's 8 over 3 times 1, all right, minus 3 times 2 all over 8 over 3. So let's see how we work with that. This is 8 over 3. Oh, 8 over 3, sorry, 8 over 3. It's a fraction. 8 over 3. So we have 8 over 3 times 1. So that's 8 over 3, 8 over 3 minus 6 over 1 all over 8 over 3. So that's like LCM at the top is 3. So that's 24 minus 6 divided by 8 over 3. That's times 3 over 8. So this cancels out. So 24 minus 6 is 18, I believe. That's 18 over 8. And that gives us that that what does that give us? Have I done something wrong? Oh, sorry. Yeah, my math is wrong. Yeah, I suspect. Yeah, my math is wrong there. So LCM at the top is 3. 3 in 3 is 1. So 8 minus 1 in 3 is 6. 1 in 3 is 3. 3 times 6 is 18. Then divided by 8 over 3, that's times 3 over 8. So this cancels this. So 8 minus 18 is minus 10 all over 8. That's like minus 5 over 4. Okay? So it means that this place now is minus 5 over 4. Now, if you look around, 8 over 3 times 0, is 0. 3 times 0 is 0. So automatically this 2 will just be 0. So we don't have to worry so much about it. So now we've got this, right? So the next thing we want to do is to find this, this, and this. Of course, as you can guess, all this will be 0. I mean, the first one only is what we're going to get a result for. So for this now, to get this part, so again, we do 5 times 4 minus 8 over 3 times 0 divided by, minus 5 over 4 times 2, minus 8 over 3 times 0 divided by minus 5 over 4. So we have minus 5 over 4 times 2 minus 8 over 3 times 0 all over minus 5 over 4. Okay, so that will just be minus 5 over 4 times 2. This is gone. This is 0 all over minus 5 over 4. This is easy because this just cancels out and we have 2. Okay, so finally our result here is 2. So the result here is 2. And if you look around, you have, minus 5 over 4 times 0, minus 5 over 4 times, minus 5 over 4 times 0, minus 8 over 3 times 0. All of this will just be 0. So we have our first column, which we need to make our final decision. So if you remember the other time, so the first column gives us the final decision. So let's look at the values we have there. So again, you can say that in the first column, okay, we have, what do we have? We have 1, we have 1, 3, 8 over 3 minus 5 over 4, 2. So we have 1, 3, 8 over 3 minus 5 over 4, and then 2. So what does that mean? This is positive, this is positive, this is positive, this is negative. That's a sign change right there, and this is now positive. So we have 2 sign changes. So this is uh first sign change. Okay. So again, we now have from minus to plus again, we have a second sign change. Okay. So because of once there's a sign change, in the first case, there was no sign change at all. So that was why we said the system was stable. In this case, um, okay, in this case now, since 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 there are two, since there are two sign changes, it means it means there are two roots. There are two roots There are two roots, okay, with positive positive parts. And once there are positive parts, that's instability, which imply that the system the system is unstable. Okay, the system is unstable. All right, so that's what we get. Yeah, with that done, let's take some practice questions talking about Routh-Hurwitz criterion. So it's a very powerful method once you can understand how the calculations go. Okay, so we can determine stability without necessarily finding the poles as it were. Okay, so let's take some practice questions. Okay, determine determine the stability stability of the systems with the following characteristic equations characteristic equations using the Routh Hurwitz Routh-Hurwitz criterion. Okay, number one, P of S equals S cubed plus 2S squared plus S plus 3. Okay, number two, P of S equals S raised to power 4 plus 4S cubed plus 6S squared plus 4S plus 1. Number three, P of S equals S raised to power 4 plus 2S3 plus 3S squared plus 3S squared uh plus 5S plus 4. Okay. S raised to power 4 plus 2S cubed plus 3S squared plus 5S plus 4. And finally, number 4, P of S equals S raised to power 5 plus 4S raised to power 4 plus 3S cubed plus 2S squared plus S plus 1. All right, so please go ahead. Let me see your answers in the comment section, either on Facebook or on YouTube. And of course, go ahead and let me know how helpful these videos are for you. And if there's a topic you'd like to teach or a problem you'd like me to solve, then I may be able to find time to get to that. If you have not subscribed to the channel, you won't, you'll be missing out a lot, right? So please go ahead and subscribe and also hit the notification bell so you can always get alerted each time a new video is released. For those who have subscribed, thank you so much. And of course, be sure to like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. So watch out. In the next video, I'll be talking about Laplace transform as it is used in statistics and probability or so. Okay, watch out. Bye.